Howdy Calculus 12.0. I'm just going to go through a couple more optimization problems. If you don't need this, then skip it. You may feel pretty comfortable about setting these up and solving them. I guess you could just try them out yourselves as they come up, and then pause the video, work them through, and then either skip to where I kind of come up with a solution to it, or watch through and see how it goes. If you need a little more instruction, then you might want to follow along as I go through it and just see how it is that I think about it and set it up. So the first one, a cylinder is inscribed in a right circular cone of height 5 centimeters and radius at the base equal to 2 centimeters. What are the dimensions of such a cylinder which has maximum volume? So we're going to maximize the volume. That's basically the entire process here. In order to do that, I kind of have to have an idea what I'm up against. So I'm going to draw my cone so that circle's on the top. That has little importance on actually solving the problem. So if you drew it other way around, that's totally fine. I'm going to put inside of this, inscribed means that it's sitting inside and kind of touching the edges of this thing. You can think of the cone as being a hollow object. We're basically going to place a cylinder in here. So the cylinder is going to kind of look like this. I'm not real good at this sort of thing, but that's the idea anyway. So we're going to place a cylinder inside of the cone. The idea is we want to make the cylinder that is going to be the maximum possible volume inside of that cone. In order to do that, we probably should understand first that there would be some really tall, skinny cylinders that would have a fairly small volume that could be in there. And you could have some fairly wide but short cylinders that would also fit in there, both of which probably have a volume that's a fair bit smaller than the one that we have right here. Now, this is not to say that this is the right one, but it's going to be more similar to what the right answer would end up being. So I've done a lot of sketching on there. Really what we want to know is what the dimensions of this particular thing are. So it has a height of 5 centimeters and it has a radius of 2 centimeters. So that's what we know right now. So I'm just kind of recording the given information. The thing that we want to find in the end is the volume of the cylinder is supposed to be maximized. So I'm just going to call it VCil. You can call it V if you want. Because the reason why I put sil in there is because it's versus the cone. There's two objects in there, so if I just put a V, it might be a little hard to keep track of things, potentially. So volume of a cylinder, it's basically a circular prism. So the base is a circle, and that circle just persists upwards the entire time. So we can just think of it as the area of that circular base, which is pi r squared, times the height of the prism, which I'm just going to say is h. So h represents the top to bottom height of my cylinder, and the r represents the radius of my cylinder, not the radius of the cone and not the height of the cone. So just to be clear, my r and my h are with respect to the cylinder. I'm not going to put sil underneath everything. I'm just going to assume that we would be aware that calculating the volume of the cylinder would use the height and radius of the cylinder anyway, so it makes sense to just leave them as r and h. All right, so we need to maximize this. Optimizing an equation requires us to be able to write the equation in terms of a single variable. Right now I have r and h, so that's not going to work out for me. Now, the trick that I'm going to use in order to come up with an equation here is a very common trick for some of these geometric examples. I'm going to use similar triangles. So let's see here, actually. I don't know if the black will show up all right. I'm going to use this big triangle right here. I'm going to highlight it a couple times. So that big triangle is constant. So it has a height of 5 and a leg up there of 2. So I basically, if I drew it over here, 2, 5. Great. Right angle up here, and it's the little whatever it is in the bottom there. Now, I am also going to draw your attention to a little pink triangle here. That's down in this section. It shares the same angle in the bottom portion. It is also a right angle triangle. It does not have a height of 5 and a radius of 2, however, it is going to have a radius of r because it is the same radius as the cylinder, but it does not have a height of h. It is actually not the height of the cylinder. It is the leftover height if you were to take the cylinder away from the 5 height of the cone. So if you, again, kind of focus on the 5 height of the cone, the top part of it is the cylinder, which has an h, and the bottom part of it is the thing that we're currently describing as part of this pink triangle. So that would be 5 minus h. So 5 being the whole height of the cone and h being the height of the cylinder. So these two triangles are similar triangles. So similar triangles allow us to develop all kinds of neat ratios. So this is how we're going to relate r and h together. And by relating r and h, we're going to be able to solve for one in terms of the other, and then use that in our volume of our cylinder equation in order to move further along in this problem. So I'm going to take the ratio of the heights. So that's going to be 5 divided by 5 minus h is equal to ratio of the base parts, I guess. So 2 divided by r. The only thing you need to make sure is that you take the same piece from the same from your similar triangles. So if I take the order from the one from the cone in the numerator, and then the one from the pink triangle in the denominator, then I can't switch it for the other side of my ratio. All right, so I'm going to, I guess, cross multiply here, get r is equal to, and then it's going to be 2 over 5 times 5 minus h. I think I am going to choose to replace the h. Now, the reason why is because it's a simpler, the squared part, if even I have a linear equation that I come up with here, which this is, r is equal to 2/5 of 5 minus h. That's linear, it's not too bad. But when I square it, it's going to become a quadratic with 3 terms. Not that that's awful, but it is going to be a little more cumbersome than if I am to rearrange it right now. Then it doesn't have to become squared because it's just the h that I'm replacing in my first volume equation. So I'm going to choose to do that. That's going to be r is equal to, let's see here, 2/5 times 5 is just going to be 2 minus 2/5 h. So I'll move things around to get that 2/5 h is equal to 2 minus r. Multiplying by 5 divided by 2, we get h is equal to 5 minus 5r over 2. Something like that anyway. And again, it's not, we could come up with a different way to describe that, but that's going to be fine. So I'm going to take this and use it as a substitution in my volume equation. So now we get volume of the cylinder is equal to pi r squared h, which h is actually 5 minus 5/2 r. And so now we have an equation that only has r in it. So I'm just going to multiply it out because we're going to take the derivative and set it equal to 0. I could do it as a product rule. It's actually not that bad the way that it's set up, but I'm going to do it as 2 separate, just really straight power rules. This is going to be 5 pi r squared minus 5 pi over 2r cubed. And so I'm going to take the derivative of both sides. I kind of gave myself not enough room there, but I'm going to say that it's 0. So I took the derivative and I set it equal to 0. So 0 is equal to 10 pi minus, and then that's going to be 15 pi r squared over 2. So again, all I'm doing there is bringing the 2 down front, multiplying with what's already there, dropping the exponent by 1, which gives me an r. Good that I tried to walk myself through that afterwards because I made a mistake. And then for the second part, you get minus 5/2 pi times the 3 that comes down gives you 15 pi over 2. Subtract 1 from the exponent and get the 2 there. So what we have now is something that actually factors reasonably well. I'm going to multiply everything by 2 first, and so I'll get 20 pi r minus 15 pi r squared. We have a 5 and a pi that can be factored out of everything. Now, I understand an R can also be factored out of everything, but basically what I'm going to do is I'm just going to divide the 5 pi over first. So that leaves me with 4r there and 3r squared there. So I'm going to divide the 5 pi out, and then now I'm going to factor my r out and leave me with 4 minus 3r. So we basically have two solutions to this. We have when r is equal to 0, and we have when r is equal to, and that would be negative 4 divided by negative 3 is going to be 4 over 3. And so we get these two solutions for the r value. Now, what this means is that we have possible maximum values at an r of 0 and at an r of 4 over 3. So the thing is, I have to think about what this volume of the cylinder is representing. R values are not allowed to be just any real number. I could have it as 0 is probably the smallest that would make sense. So I'm going to test r of 0, which I would have, an r value of 0 in my volume equation, which I would have anyway because of the solution that we found. I'm also going to test an r value of 4/3. That's pretty messy. 4/3. And then last, I'm going to test an r value of the top end. So I can't extend that r outside of the actual cone that we begin with. And that cone has an r value maximum there. If we went all the way over and just had the thinnest cylinder ever, it would be 2. So I will attempt to put in a 2 as well, although we know that the volume should be basically non-existent because you can't have any height there. So if I were to use the original equation, I'm going to take this one actually because it is in terms of r, and as long as I didn't make any silly mistakes between the first line and the second line, which double checking looks okay, then should be able to plug in these values and then we can test to see if it was okay in the end. So if I put an r of 0, I end up getting 0 minus 0. So that is not surprising. We would get a volume of 0 for r of 0. I'm going to use the 2 as well. I'm going to do that right now. So that's 5 pi times 2 squared, which is 20 pi, minus 5 pi times 2 cubed, which is 8. So that's 40 pi divided by 2 is 20 pi. So 20 pi minus 20 pi is 0. So that also gives us a 0. Also no big surprise there. Next up, we're going to get a volume that is going to be something different because it's the 4/3. Now, I guess I could just write it in. So it's going to be 5 pi times 4/3 squared minus 5 pi over 2 times 4/3 cubed, which probably should just take that and move it down. Does that no? Oh, that's so bad. All right, so let's take it with everything, and then let's go and evaluate that. So 4 squared is 16 times 5 would be 80. So it's 80 pi over 3 times 3 is 9. And then on the other part we have 4 cubed is 64 times 5 would be 320. So I think it's 320 pi over, and then 3 cubed is 27 times 2 is 54. And there is a 2 that's in common on that other one. There are no common factors in the first one, so I'm stuck with my 80 pi over 9. I could divide both those by 2, so get 160 pi over 27. And then I could put them both over 27. I guess I'm just doing all this by hand just because. 240 pi over 27 minus 160 pi over 27, which gives us 80 pi over 27 as a volume. So apparently, hopefully, that is a lowest possible volume. Now, maximum. That's the highest possible value. We know the lowest is 0. One of them is a boundary, and the other one was a boundary slash. It showed up as part of the local minimax possibilities. So if we this is closed interval, so put a little line on either side. So this is for our R values of 0, 2, and then 4/3. What we ended up finding out was if we use we didn't test first derivative test yet, but I could. So if I take this thing right here, which is the first derivative, and I assess what would happen if the r value here was 1, which is to the left of the 4/3. So if the r value was 1, I would get 10 pi minus 15 over 2 pi, which is 7.5 pi. That's going to be positive. So we would have positive on this interval. If I was like on the other side, which is really close to 2, I probably could use 1.5. I don't know if I'll be able to do this mentally very well. So it would be, the first part's not too bad. So that's 1.5 times 10 would be 15 pi. So we just need to make sure the next part's not 15. So, or it's going to be greater than 15. So you'd have 1.5 squared is 2.25 divided by 2. That's a number bigger than 1. So you are going to get an overall negative. Test it with the values if you'd like to. So you get a positive on the interval to the left this is for the first derivative test. First deriv. I'll just put that. So we go positive to negative, which means that this is a local max. So this is definitely good that we found that, and this is probably, hopefully, if everything's gone well, 80 pi over 27 should be the correct answer for the maximum volume. Now, if I had read the question properly, it doesn't actually ask me to find the maximum volume. It asks me to find the dimensions, which we found the dimension for the radius would be 4/3, and that would be in centimeters. And then we would find out what the height was. I'll back up into where we came up with that equation for the height, which is 5 minus 5 halves r. So 5 halves r, 5 halves of that would be 26, so 10/3, and 10/3 taken away from 5, so 15/3 minus 10/3 would be 5/3 centimeter. All right, so hopefully that's correct. We'll test it out here in just a moment. So let's pull up the iPad and the graph. So here we go. Now this it does depend on one thing. I need to have done this correctly for this to actually tell me if I did everything past it right. So hopefully our similar triangles, we didn't make a mistake there, because if we did, then it's possible that the answer is actually wrong. Because what I'm going to do is I'm going to use this highlighted box right here as an equation that just represents our volume. So I'm going to do y's and x's instead of v's and r's. But if I did y is equal to 5 pi x squared minus 5 halves pi x cubed. And so this, if I subbed in correctly for the height, then this cubic is representing the volume at any particular point in time. Now, we of course get 0 at 0, and we get 0 at an r value of 2, which we said was kind of our boundary conditions. One of them was also a local minimum, which you can see on the cubic. That makes sense. So we're hoping that this spot right here, which is the maximum volume, is going to occur specifically. This is for r, the equation, so this should be at 4/3, or 1.333. So 1.333, it's good. So it appears to have worked out pretty well. Now, it also tells us the volume there, which I said was 80 pi over 27. So that's like pi times 27. 81. That's really close to 3. So it's really close, a touch over 3 times 3.14. So it'd be like 9.5 something. Well, a little bit less, I guess, because it was a little bit less than 1. Or a little bit less than 3. So that seems to make sense too. I mean, I could put it in. So we'll do 80 pi divided by 27. And so, yay, we get that same number. So that looks good. So this was a little more weighty geometric example, I guess. I'm going to talk about something early on. Now, I consciously, and I told you as I did it, made the decision to sub H out and put R's in. If you do this the other way around, it it'll give you the right answer, but it is a fair bit more icky in the middle. So this one you could mostly do with mental calculations. There wasn't anything that got really out of hand in terms of the numbers, although grab a calculator, that's fine. But yeah, that's that one. So one down, one to go in terms of what I'm going to show you here. All right, so cylinder inscribed into a right circular cone. Next up, cable TV company is going to be laying cable in an area with underground utilities. I'm pretty sure because of the big numbers here, I'm going to need a calculator. Oh, I have one. I actually didn't know I had a calculator sitting around. So that's good. All right. So cable television company is laying cable in an underground area with underground utilities. Two subdivisions are located on opposite sides of Willow Creek. Okay, so I have Willow Creek here. And Willow Creek is 100 meters wide. The company has to connect points P and Q with cable, where P is on the north bank, Q is on the north bank, east of P. So this would be Q on the north bank, and it's east of P. So go back to the west, and this is P. So it's 1,200 meters east of P. So if we were to measure the distance between being directly across the other side, that would give us our 1,200 meters there. So the company has to connect points P and Q with cable. It costs $40 per meter to lay cable underground and $80 per meter to lay cable underwater. Okay, so I'm going to do underwater in blue. So I could come straight across because that's expensive to lay that cable. It's twice the cost per meter to go underwater. So that's expensive cable. And then I could go, let's do brown maybe, underground here. Whoa. The rest of the way. And that would be one option for laying cable. Now, I could also think about minimizing the total distance. And so I might want to just go right from P to Q. That's a smaller distance, which is good, but it's really expensive cable, which is bad. Just by eyeballing, my guess would be from the geometry that's going on here, even though this is not to scale at all. So maybe that's a kind of a crappy thing to say. My guess, though, would be that P to Q directly would probably be more expensive than P straight across and then go along the ground. However, there may be a little way to cut a corner here and then go the rest of the way under the ground and have it be even cheaper than that option. So I have to keep that kind of open and in mind as I do this problem. So we could think of going from P to Q. So this is like, let's say this is root A and this is root B. And then we are going to have this kind of flexible one, which is root C. And I'm going to try to minimize the cost of root C. But I'm also going to keep in mind kind of like these boundary conditions. It would be really dumb to go back this way then come down. That doesn't really make much sense. And it would be really bad to come down this way and then come back because you're just tacking on extra distance for no real reason. So let's just calculate what the cost of A would be. So the cost of A is going to be so it's 100 meters this way and it's 1,200 meters that way. So it's going to have a distance of Pythagorean theorem. So I'm going to just do that on my calculator. So it's 1,200 squared plus 100 squared. And I'm going to take the square root of that and get that it's 1204.2-ish. 1.6, but that's fine, 2. So at a cost, and I'm not going to round yet, I'm actually just going to multiply by the value first. At a cost of $80 per meter, that is going to give us a grand total cost of $96,333.76. great. I mean, I have no clue what that's compared to, so who knows whether that's expensive or not yet. Let's do cost of B, just to kind of get an idea there too. And then so B is easier to calculate by hand because we're just going to actually go the 100 meters with the expensive cable. So that's going to be 100 times 80, which would be 8,000, plus we're going to go the 1,200 meters at $40 per meter. So that would be 48,000. Okay, so significantly cheaper to go straight across and then down. So we get $56,000 as being the, I guess, amount that it would take to go on B. Now, if we didn't have access to calculus, we could kind of use some test values in the middle, but we can do better than that. So what we want to do is actually say, when we do the diagonal first step here, I'm going to say that we're going to aim for a spot on the shore that is X down from being straight across. So what that's going to mean is we have that the river is 100 meters wide, and we're going to aim X down. And so this part here is going to be the underwater. So I'm going to call it W for water. And then from there on out, I'm going to have 1,200 meters to go minus the X that I've saved by going diagonal. So it's going to be 1,200 minus X left. So I can get W in terms of X by using Pythagorean theorem in my first triangle, and I already have the other length in terms of X. I could have set it up, I guess, by calling it like Q or something else, or not Q. I guess Q's already in the question. Something different in the meantime, but we kind of avoided having to do that by just saying 1,200 minus X. So the distance W is going to be W squared is equal to 100 squared plus X squared. So that's W. So it's W is equal to the square root, I guess, of 100 squared plus X squared. All right. So total cost. Our cost by going this path, which I'm just going to call C. So cost C is equal to the distance that we go underwater times the cost of the underwater, which is 80 per meter, plus the distance that we go above ground, or sorry, underground, times the cost of going underground, which is 40. All right, so I get to do a derivative, set it equal to 0, and solve for where that occurs. So C prime is equal to 0 is equal to, 80 is a constant multiple. The 1/2 comes down front because that's a 1/2 exponent. I leave the inside alone, which is 100 squared plus X squared. Now to the power of negative 1/2 times the derivative of the inside, which is 2X. Now, for the next part, we're going to have a very, very simple derivative. So it's 1,200 minus X is just minus 1 times the 40 that's there, constant multiple. So I'm going to move that right over. So that's going to be a positive 40 instead of the 0. So I'm just adding 40 to both sides. And then I have the 80 times 1/2 is 40 times 2 again is 80. So we get 80. And then also up top is going to be X over top of the square root of 100 squared plus X squared. So I'm going to multiply my square root up onto the other side. Square both sides to get rid of that square root. So it's going to give me 1,600 because that part gets squared as well, times the square root goes away, is equal to 6,400 X squared. All right, so 1,600 on the left, 6,400 on the right. You can divide that out and get a much smaller value, which I'll do. So that's going to be 4, right? Yeah, 4 x squared. And so now I'm going to get, I'm going to actually square out the 100, and I don't need a bracket there anymore. So that's 10,000 is equal to 3x squared, or 10,000 divided by 3 is equal to x squared. That would be, well, 100 over root 3. I don't care about negative values of x, because that doesn't really make a whole lot of sense. That would mean for me that it would be back kind of in the other direction. I don't think that's worth really getting into. So I'm not going to bother. That would mean, whoops, sorry about that. So that would mean that we have root 3, 100 root 3 over 3 is our x value. Now, just to give you an idea of what that is as a number, I'm going to punch it through the calculator. So that would be 100 times the square root of 3 divided by 3. So that gives us an x value of 57.7 meters. So that's not a very large amount compared to our diagram. So it is a fairly small x, because we don't want to, the more we bend it over, the more underwater we have to go. But it does save us a little bit of kind of like total distance while not adding on a lot of underwater. So let's see what happens if we evaluate the cost of the entire thing when using a 57.7 meter x value. So, oh, that's a little bit funky. I guess I can use this equation right here that's already set up for it. So I'm going to just fire that through. I'm going to do it on Desmos so you can see the calculation as opposed to just me doing it on the calculator that's in front of me. No, I want to do this one. So let's do square root of 100 squared plus x squared times 80 plus 1200 minus x times 40. And I'm going to call this the c of x function. And we want to evaluate specifically, now just to double check it, we said c of 0 because this would be very helpful in knowing that we had set this up right. So if I did c of 0, because we did that before we ever came up with that equation, that is if we cut straight across and just have no x value. So that's 56,000. That looks really good. And then we could do c of, if we went the whole way, that would actually be an x of 1200, because it would be all the way down to the end, which is 96,322 and 76 cents. Great. So that is also good. So this bodes really well in terms of this equation with the cost seems to be good, because we basically did the first part a little bit separately, or at least we did it twice in kind of the same way, one general and one not. So now here's the moment of truth. We want this thing that we found is either a local minimum or a local maximum. It wouldn't make sense for it to be a local maximum, because that would mean it was the highest possible cost. And that just doesn't make sense from kind of the setup that this 57.7, which is kind of like path C, would be the highest possible cost. We could double check that by using the first derivative test, which is a really good idea. You should do that all the time. I'm going to be a little bit lazy and not do it this time, just to make the things a little bit shorter. And we're going to finally do it. So C of 57.3, was it? 57.7. All right, 57.7. That is $54,928.20. So depending on your point of view, because you had to pay a mathematician to do this, or a high school student, I suppose you could have done it for, 15 minutes of work. That's pretty good hourly wage if they're willing to give you a portion of the savings. So the savings there are approximately $1,071.80 or something like that. So yeah, it's it's worth it. It's worth it to do that, cut across, and then down the rest of the way. Now, this is all well and good. Does this thing actually, does it make sense in terms of the values? Now, so I could have scaled a little bit better. So let's talk about how to scale a graph appropriately given information that we know. So the x values that we're interested in are x values between 0 and 1200. So I'm going to put negative 100 just to give it a little bit of stuff on that side. I'm going to go 1300 again just to give it a little bit of a boundary on the other side. We know that the costs seem to be somewhere between like 50,000 and maybe like 100,000 is what I'll put in, because we had 90 something, I think. So 50 and 100. All right, so that is a much nicer graph to look at. I can zoom out a little bit there. So it's interesting. This is the point that we said was cut straight across. At 1200, whoa, we're way up here somewhere, and this is much more expensive. So that was the total underwater. The rest of the graph kind of wouldn't exist. We could put a domain on it, Desmos, and that would be nice. And then this magic little point is what we found using the derivative, 57.7. So that's good. So there's another example. Uses some geometry, specifically Pythagorean theorem, and gets us an answer that looks pretty good, at least when we check it using some stuff in Desmos there. So hopefully these ones a little bit longer, maybe a little bit more complicated. Do lots of practice. I find them really fun. I think that these are interesting questions to kind of pick away at and spend some time on. You will get more and more comfortable with them the more that you do. Some of them require some sense of things that you may not have enough exposure to feel comfortable with. That's okay. Take a deep breath, try them out, see how they go. If you get stuck, move on to another one. If some of them don't set up real well in your eyes, that's okay. I wish you all the best. If you're having some trouble setting something up specifically in your practice and you want to have a chat about it, just fire me off an email or something. Let me know. Take care, FHS.